Hello, welcome to our special fall break edition of Fluid Mechanics, where we're going to fill in some lecture material that we missed yesterday. And today I'm going to talk about the continuity equation in a little bit more detail. First of all, though, some housekeeping. We do have some assignments coming up. Homework number 17 and worksheet number 18 are due next Monday, and homework number 18 and number 19 due next Wednesday. And we tentatively have a quiz scheduled for next Friday. First, our regular segment on fluids in the news. Since yesterday was a rather unusual and magnificent event, as one of the strongest hurricanes to ever hit the Gulf Coast came through. We talked about this earlier in the week when it was still just a small tropical storm, but with the potential to grow. And indeed, Hurricane Michael turned out to be the third strongest hurricane to ever hit the U.S., the continental United States. And a little bit of data on it. You can see how it rapidly intensified. I've plotted two different variables here. The red line shows how the wind speed increased over the course of the day yesterday from midnight on the 10th till midnight last night, the night of the 10th into the 11th, as the winds grew to 155 miles per hour. And as we discussed before, an even better indicator of hurricane strength is the pressure at the eye of the storm. And here I've got that plotted. You can see that it hit a minimum around noon as it came on shore and dropped just below 92 kilopascal. So compare that to 101.3 for our typical conditions at sea level. And you can see that it dropped below Hurricane Katrina levels. So this was an extremely powerful event that came on shore, and the full extent of the damage is just now beginning to be assessed. The positive, if there was one, is that it hit an area that has a relatively small population, no major urban centers, and also it was a very fast-moving storm. So unlike Hurricane Harvey last year and Hurricane Florence that hit North Carolina just a few weeks ago, those two events sat there and stalled and dumped huge amounts of rain. This one, although very powerful, moved through quickly and therefore didn't cause as much flooding. Back to our main material, though, we're going to continue talking about the conservation equations. First of all today, by wrapping up the continuity equation before we move on to the momentum equation next week. And your next worksheet assignment is actually associated with the momentum equation, starting to get comfortable with that theory before we wrap up with the energy equation. So last time we derived this equation, the continuity equation, and it's a very simple derivation now that we have the tool of the Reynolds transport theorem to work with. So all we had to do was recognize that by identifying the extensive property, the capital B, as mass, and therefore the intrinsic property, little b, as being mass over mass, which equals to 1. Substituting that into the Reynolds transport theorem, very easily we arrive here at the continuity equation. And the other thing to recognize is from the conservation of mass principle, that for a closed system, mass must be conserved. Therefore, the total derivative of the mass with respect to time is equal to 0. So there we are. We've got our continuity equation. So that part's pretty simple. The hard part is figuring out how to apply this, and specifically the trickiest part is learning about which assumptions are appropriate as we address different problems, and then being able to simplify this equation based on those assumptions. So that's what we're going to work on today. Oh yeah, and first I wanted to really emphasize that this first term here, with respect to time, is telling us how mass is changing within this stored volume, represented by the differential volume over here. And the second term is representing how mass is moving into or out of that control volume across the control surfaces, represented by this differential area. The first assumption I want us to consider is that when we have flow that is normal to our control surfaces. So here I've got an example where we've got flow entering our control volume on the left, exiting on the right. This might be a pipe, it might be an open channel. but the point is that the flow is coming in perpendicular to these control surfaces on both sides. So if we look at our equation, what that does for us is the dot product that we had within our control surface now goes away. We don't have to worry about that dot product anymore because v dotted with a normal vector that is perpendicular is just equal to the velocity itself. We do, however, need to keep track of what flow is coming in and what flow is going out, because the dot product was also providing that service for us, because recall we had our normal vector pointed outwards. So flow that was coming in had a negative sign on it, flow that was going out had a positive sign on it. So if we take that all into account, we end up with an equation that looks like this. It looks a little bit more complicated because we have added an extra term now, because we're keeping track of what's coming in and what's going out. But in reality, this is easier to deal with. We don't have to worry about the trigonometry or this dot product associated with those control surfaces. We just add up what's coming in and what's going out. The next assumption that I want us to think about is that of uniform flow. The point is, as indicated by these arrows that I've drawn on either side of our control volume, that we have flow that can be represented just by the average velocity coming in and the average velocity going out. So when we do this, we no longer need to worry about that integration sign. We can just sum it all up. So our integrals for the flow across to the inflow control surface and the outflow control surface can just become summations, and we end up with a form of the equation that looks like this. Don't worry about the fact that I changed the order of these two terms around. I was just copying and pasting from various places. But the bottom line is we've got still a change in the mass within our control volume. We have flow that is exiting, which has a positive sign on it, flow that is entering, that has a negative sign on it. Note in this particular case, though, that I've just taken my equation from before and modified it, and we had already assumed that the flow was normal to the control surface. These conditions don't need to be additive. We can have a condition where we have uniform flow, but uniform flow that is not normal to the control surface. So you need to be able to kind of pull these together and break them apart. I'll give an example of that in just a bit here. The next condition that I want us to consider is steady flow. And this one hopefully is becoming pretty obvious to you, but the idea is we've got this term over here that is our unsteady term. It's how things are changing within our control volume. And if we had steady flow, as hopefully you already connected here, we don't have to worry about that term anymore. We don't have a change within our control volume because things aren't changing with respect to time. So we're still maintaining our fluxes in and out of our control volume, but we're not letting things change with time anymore. Okay, so we end up with a form of the equation that looks like this. This is, however, where I want to point out that I've been just building my assumptions on top of each other. So the equation right here up above assumes now that we have uniform flow, we have flow that is normal to our control surfaces, and we have steady flow. But we can have any of these independently. So let's assume that we had steady flow, but we don't have flow that's normal to control surfaces. We don't have flow that is uniform across our control surfaces. What would that equation look like? Well, it'd look like this, right? Where I go back to my original equation, I still drop out the same term, the one that's changing with respect to time, but everything else is still in there. I still have my dot product. I still have my integral. So this would represent the equation for steady flow, but one that does not have normal flow, does not have uniform flow. And we're going to talk next about incompressible flow. This one would not be assumed incompressible. We still have a density hanging in there. So let's talk about that. And when we talk about incompressible flow, that's really more of a catch-all to say that we have flow that has a uniform density throughout the system. So we could, for example, have flow that we consider incompressible, yet we have two different fluids with two different densities. This assumption applies across that entire field of assumptions. So bottom line, though, is if we can consider the density to be constant throughout our system, we are able to get rid of our density terms. So we drop the density and we end up with this nice simple relationship. Again, this particular equation then would say, would be based on the assumptions that it's incompressible and normal to the control surface and uniform across the control surface, and steady, right? Those are all built into this. Okay, so could we have this condition and still have unsteady flow? Sure, right? That might look something like this. We could still cancel out our density terms because we're saying that the density is consistent and uniform throughout our entire problem, but things are still changing with respect to time. When those densities go away, we're now integrating a volume across our entire control volume. So that simply becomes, how is our volume of our fluid changing with respect to time, which is going to be balanced by flow that is leaving our control volume and flow that is entering our control volume. Okay, let's continue to work through some examples, and I'm going to go through the solutions to the worksheet that you turned in on Wednesday. So, and I'm going to go slightly out of order because I want to start from simple and make it more complex. And the third problem that you answered on your worksheets, which looked like this, was actually the simplest form of the equation. Now I want us to think through, all right, what assumptions are necessary in order to arrive at this form of the continuity equation? And it looks really simple, so yeah, all of them are going to need to apply. So let's come up with a systematic way to think about that, though. So let's go through them each, and then I'll try to help deliver a trick here for you to remember them. So first of all, we know that flow is normal to the control surfaces because we don't see a dot product in here, right? We don't have V1 dot n, we don't have V2 dot n. So we must have flow that is normal to the control surfaces in order to use this form of the equation. Similarly, flow must be uniform across the control surfaces because we don't have some type of an integral that is reflecting how velocity is changing along that control surface. We just have a v, right? So we must have flow that is uniform uniform across the control surfaces. We don't see anything changing with respect to time. The partial with respect to time is gone. So the flow must be steady. We don't see density in this relationship, so we must have constant density throughout the system in order to use this form of the equation. And we have this A1 V1 equals A2 V2, which implies that we must only have one inlet and one outlet. Okay, so this is the full range of assumptions that we can possibly apply to the continuity equation, and it allows us to arrive at this very simple version of the equation, which of course you'll remember we used back in chapter 3 when we were first learning about the Bernoulli equation, when we were keeping things really simple. So yeah, this is super simple. That said, this is still a really powerful form of the equation. It applies to a lot of situations. Often when we're dealing with pipes and pumps and open channels, etc., we'll be able to use these assumptions, and we'll be able to use this very simple form of the continuity equation. Of course, it's not always the case, so that's why we need to be able to use it in a more sophisticated form as well. So here's a trick that I just developed. Came up with this simple mnemonic here of NUSI11. Okay, so as you're thinking through what assumptions might be applicable, I encourage you to just go down this list of NUSI11. So is it normal? Is it uniform? Is it steady? Is it incompressible? And do I have one inlet and one outlet? Okay, and that way you've got just a systematic list to work your way through. Now the trick is saying, okay, first of all, when can I assume it's normal? And if I assume it's normal, what does that do to my equation? And then doing that for all 5 of these potential assumptions. Okay. All right. So let's look at another one. This was the first problem on your worksheet. And let's see. What do you think? Let's work through each of them. So first of all, do we think that the flow was normal? Assumed to be normal to the control surfaces. I don't see a dot product, right? There's no normal vector in here. So yes, in order to use this equation, we are assuming that the flow is normal to the control surfaces. Is it uniform? Yes, we don't have an integral. We don't have some form of the velocity with respect to distance along the control surface. So we're assuming uniform flow. Are we assuming steady flow? Yep. No partial with respect to time. But we're not assuming incompressible flow, right? We have held on to our density terms here, so we can have a different density on the outflow versus on the inflow. So we're not assuming incompressible flow or constant density through the system. And we're still summing up our inlets and summing up our outlets. So we can have more than one inlet, more than one outlet, whatever we want. So we are not assuming one inlet and one outlet. So we are assuming normal flow, uniform flow, and steady flow. All right, let's look at problem number 2 from your homework, from your worksheet. Reflect on this just a little bit. Let's go through our UC1 one. Okay, do we have flow that is normal to the control surfaces? Well, I guess not. I jumped right to steady. We're not assuming that it's normal to the control surface because I've got this dot product in here, right? I'm able to adjust for it if I have flow coming in at an angle. I can take the dot product, so I'm not assuming that it's normal. Uniform? No, I've kept in my integral here. Okay? So I'm able to set up my velocity as some type of a function of distance. I'm able to break it up into different components. For example, I could have a pipe with a maximum velocity in the middle, no slip out on the outside, add that up. So I'm not assuming that I have uniform flow across my control surface. Steady? Yeah, we are assuming steady. We don't have a partial with respect to time here. We only have a term that's representing our flux across our control surface over our differential or integrated area. So steady. We are definitely assuming steady flow. And then the last term that we were considering is whether or not it's incompressible. We're leaving our density in here, meaning it can change across our system. So we haven't assumed that we have incompressible flow. So the only assumption that we have made in order to arrive at this form of the equation is that it's steady. And we haven't assumed any of those other things: normal, uniform, incompressible, one inlet, and one outlet. All right, number 4 on your worksheet was a pretty long-looking equation here. So hopefully this is starting to click, and you can just look at this and say, all right, what am I missing? What has been changed about this equation from that original form that we got from deriving the Reynolds transport theorem? And hopefully what's jumping out at this point is we're not seeing any dot products, right? And what was the dot product associated with? Normal flow, normal to our control surface. So as we go through our assumptions, we have to assume the flow is normal to the control surfaces in order to apply this particular form of the equation. Okay, anything else? No. Okay, we still have all the other terms represented here in one way or another. So that's it. All we've assumed is normal flow. This can be applied to flows that are not uniform, not steady, not incompressible, with multiple inlets, multiple outlets, etc. But the flow needs to be normal to the control surfaces. All right, and I believe this is the last one from your worksheet. This is number 5, and again, hopefully you're starting to hit these pretty quickly. It's just kind of popping out. What are we missing? Looks like we're assuming normal flow, and something else has changed. The density term is gone, right? So we're not assuming that we have incompressible flow, or in other words, that the density is uniform throughout our entire system. So we are assuming normal tangential flow, and we're assuming that it's incompressible, or that the density is constant throughout our system. We don't need to assume uniform flow because we still have these integrals. We don't have to assume steady, and we don't have to assume one inlet and one outlet because we're able to sum this up over multiple inlets and outlets. And again, keeping track, if we got rid of our density because we're assuming that it's constant throughout, instead of having a mass term over here with the time derivative, it has now become a volume term because we've taken the volume, divided it by density, or sorry, taken a mass divided by density, and that is equal to a volume. So how's the volume changing with respect to time? Okay, so with that, I want to switch gears and look at how to apply this more systematically to solving problems. So I know you already had a homework problem set with fairly simple applications of the continuity equation, so I wanted you to kind of take a stab at solving these types of problems. But now that you have that practice, I want to spend a little bit more time thinking about this in a systematic way. And these are the steps that I strongly encourage you to follow when you solve continuity problems. And when solving continuity problems, the challenge is that it's kind of easy sometimes to jump forward to a conclusion just based on logically looking at the problem, because continuity equation is fairly intuitive. It's not very hard for us to physically picture what is happening, but things are going to get harder, especially as we step into the momentum equation, which is next step on our plate. It's not intuitive, and we want to follow these exact same steps. So we want to develop those good habits now, so that we can jump into the momentum approaches without stumbling. So here are the steps I want you to go through. First of all, always draw a control volume first. If you aren't able to describe exactly what your system is and what control volume that system is passing through, you can't systematically solve these problems, and you're also going to miss some potentially valuable partial credit come exam time. So I don't see a control volume. You better get the problem right. Next is to label your control surfaces. So what is the flow crossing? Okay. Next, go through and state each of your assumptions. So apply my NUSI 1-1. Okay, is it normal? Is it uniform? Is it steady? Is it incompressible or steady density? And how many inlets and outlets do we have? Can we get away with just describing it with one inlet and one outlet? Then, once you've identified all your assumptions, write down the appropriate form of the continuity equation. And then finally, you can jump into solving it. So I know there's a tendency, for whatever reason, people really like to just jump into it, start putting down numbers, and start plugging away. That might work sometimes, but I really encourage you to go through it in this more systematic fashion. Okay, so let's set up these different homework problems. So this should help you a lot come Monday morning at 9:35 when you're trying to finish and upload your homeworks. I'm going to help you set each of these up, but I'm not going to solve them for you. I want you to take them to the finish line, but I do want it to be really clear how we deal with these assumptions and setting up the right equation. All right, so our first one looks like this, and what I again encourage you to do is take a look at this and let's work through the homeworks together. So take a stab at it. Read the problem carefully, look at it, think about how you would solve it, pause this video, give it a shot, and then either check, did you do it the same way that I suggested that you do it, or if you don't quite get how to do it after you've given it some thought, then take a look at how I suggest that you go about it. Anyway, I encourage you to challenge yourself, not just listen to me, because I won't be there for you later in life, including during the exam. So, step 1, draw a control volume. Okay, please draw a control volume. So for these continuity equations, for applying the continuity equation, it's usually pretty simple to identify our control volume. It gets harder with the momentum equation. So again, a good reason to practice so that it's not quite so intimidating a little bit down the road. But here's what I suggest. Okay, pretty simple. We're just going to use it. We've got flow passing through a T or a Y in a pipe. So I'm just using the inner wall of the pipe as my control volume, and I have identified 3 different control surfaces that I have numbered 1, 2, and 3. Okay, so now I have my control volume and I have my control surfaces. Okay, next up, assumptions, right? I'm going to go through my NUSI 1-1. Is it appropriate that I assume that the flow is normal to the control surfaces? Yes. Okay, pretty clear in this case. It's coming down the pipe and then it's continuing down the pipe. The flow doesn't even have the ability to move lateral to my control surfaces. So yeah, normal. Uniform. Yes, in fact, in this case where I've got something designated just using a flow rate, Q, we have to assume the flow is uniform because we don't have any information about the velocity in the areas. We only know Q. So we're assuming that there's some generic uniform velocity is appropriate. Steady, yeah, we don't have any information about this changing with respect to time, so it would be appropriate to assume that we have a steady flow. Incompressible, what do you think? So we've got two different fluids mixing, we've got a specific gravity. That tends to make me think that this is not going to be considered a constant density. So it's not going to be appropriate to consider this to be an incompressible flow. Okay, so there's our NUSI. How about one inlet and one outlet? No, obviously not. I've got two inlets, so that assumption is out. So the equation that I want to set up is going to be one that will represent normal, uniform, steady flow. I think that looks like this. Okay, especially I've gone ahead and adjusted this a little bit for the fact that I've got two inlets and two outlets, but my unsteady term is gone, my dot products are gone, my integrals are gone. I could have written this as a summation of the summation of in is equal to the summation out, or summation out minus summation in equals 0, but I've just jumped forward a little bit from that and just recognize that on my left here I've got all the inflow, and that has to be balanced by the outflow. But further, like I was saying, if we're making this assumption that I've got a uniform flow across each of my inlets and my outlets, and I don't even know the details in terms of, I don't know the velocity in, I don't know the area in, I just know that I have a Q in here and a Q in down below of my alcohol. Yeah, I can just substitute that in. Okay, so I've got a density of water multiplied by a flow rate of water, a density of alcohol multiplied by the flow rate of alcohol, and a density of my mixture going out and the flow rate going out. Okay, and the way you're going to go about solving this is that, well, Q1 plus Q2 has to equal Q3, so now you can back out what your density is of your mixture. Okay, let's look at the next one. This one, what do you think in terms of our control volume? We've got two rivers that are coming together, so I'm just going to represent the control volume as that river itself, and the edges of that control volume being the banks of the river with the upstream and downstream cross sections. Okay, and I'm going to point out why I wrote this as 4 control surfaces when it appears like I really kind of have 3, right? I have 2 inflows and an outflow, just like the last problem. The point here being, though, that my control, my velocity across the outflow is not uniform, and I'm applying a little bit of a trick here. Okay, so let's go through our assumptions now. Is the flow normal to the control surfaces? Yep, it's all flowing right in and flowing right out. Is it uniform? No, not really. Not across the entire outflow. But again, I've gotten a little bit clever here in terms of how I've represented that outflow. I've broken that up into 2 different control surfaces out, 3 and 4. It is uniform across 3. It is uniform across 4. So even though in the problem statement it described this non-uniform velocity profile, I'm able to set up my control volume and control surfaces in kind of a clever way, and I'm back to uniform flow. Okay, and it's also steady. We don't have anything going on with respect to time. It's incompressible. There's no information about the density, temperatures, or anything like that. How about one inlet and one outlet? No. Now we have 2 inlets and 2 outlets. Okay, so take our original continuity equation, break it down a little bit, and pretty simple, right? I've got 2 inflows, A1V1, A2V2. I've got 2 outflows, A3V3, A4V4. So I've got one equation here, but I still have 2 unknowns. I'm trying to solve for the velocity. I still have this V3 and this V4. So, a little hint here that we can set up. We recognize that V3 and V4, we know how they're related to each other. We can derive another very simple equation there to represent V3 with respect to V4. Now I've got 2 equations, 2 unknowns, and you should be able to solve for V. All right, another problem. Okay, again, I encourage you to kind of read this carefully, pause it, give it a shot, and then listen to what I have to say to give you a little bit of advice rather than just barreling right through this video. Okay. What do you think? What should our control surface look like? We've got a side view of an open channel. Suggest you make it look something like this, right? Where I've identified this reach of the channel where we're trying to solve our problem. And now let's think our way through our assumptions again. All right, first up, is the flow normal to the control surfaces? Yeah, it looks like it, right? We have velocity just in the U component, just in the X direction. We don't have flow that's going up and down. We don't have flow that's coming into and out of the PowerPoint here. So yeah, normal to the control surfaces. How about is it uniform across the control surfaces? Well, at cross-section 1 it is, but at cross-section 2, no, obviously not. We've got this velocity that's a function of distance from our stream bed, designated as y. So nope, it's not uniform. We're going to have to deal with that. Okay, is it steady? Sure seems like it. Nothing going on with time here. Is it incompressible? Yep. Again, no information about the density, temperatures, or anything like that, so should be safe to assume that we have incompressible flow. And do we have one inlet and one outlet? Yeah, we do. All right, we just have one channel flowing in and flowing out. So this is what I came up with in terms of expressing the continuity equation. Right, we got rid of our unsteady term, but we do have an inflow and an outflow. They're going to have to be equal to each other. At the upstream end, it's really simple. It's just going to be V1 times A1. But at the downstream end, it's a lot more complicated because we've got this power law describing the velocity profile. So we're going to have to integrate that over the area. And to take that a step further, because it's not exactly clear at this point, it's a little bit complicated because we've got this u that's changing with the function of y, but we need to integrate over a, which is the control surface area over here, which is 1 foot deep and let's see, how far is it going into the board? 3 feet into the board. So what we're going to do is recognize that since we have a channel that is a constant width of 3 feet, we're going to call that B. That's a common abbreviation for the width. And we can break that out like this, okay, where I've plugged in now that I've got a velocity u, and I know the equation for the velocity u. So plug that in, and then this dA, I've broken it up, recognizing that b is just a constant. So instead of integrating over the area, I'm just going to integrate over the depth, and we're off and running. Okay, so you're going to take that and see if you can back that out in order to find, I guess it's the velocity that you're trying to solve for. Okay, the last problem. This is a really good example of where you could probably just logic your way through this. Probably just look at this for a little while, come up with the right equation for volume of a cone, do a little unit conversion, and figure out, all right, how long is it going to take to fill up this cone? But I'm asking you not to do that. I want you to really think your way through this, how it applies to that fundamental relationship. Again, the payoff is down the road, that when we get into more complex problems, especially in the momentum equation, that you're able to deal with the complexities. So, control volume. This one is actually pretty interesting because our control volume, we could just make it the cone, and it could work, but if we're keeping track of mass inside of the cone, and we've got two different fluids, we have, I don't know if it's water coming in, I guess it doesn't tell us, but we've got some liquid that's flowing into the cone. And then we also have, so that's down here on the bottom, and then we have this head space that's full of air apparently. Okay, if we keep the entire control volume as being this entire cone, we're going to have to account for both of those fluids somehow. Okay, it's doable, but maybe more complex than we need it to be. So instead, what I suggest is that you make this a deforming control volume, where the control volume is just tracking up. As the cone fills, the control volume is increasing until it finally becomes the entire cone by the end of our problem. Okay, so let's see. So there's my suggestion for a control volume. I didn't label the control surface, but the control surface is where the water is entering at the top. Right? Okay, so let's go through our assumptions. Nusi, okay. First of all, is it normal to the control surface? Yeah, that seems reasonable, right? We're dumping it in from the top, it's flowing down, just flowing straight into our control surface. We're not going to worry about any dot products here. And the bottom line is that anything that comes out of the hose, all of that mass, it's coming into our cone here. None of it's going out towards the side, so that's reasonable. Is it uniform across the control surfaces? Okay, this is, again, I want to spend a little bit of time on this because, quick answer would be no, right? It seems to be flowing in just towards the middle. It's not evenly distributed across this entire circle that represents the top of our control volume. That said, the answer is yes, because we are trying to track the amount of mass coming into our system, and we don't have some complex distribution here. Anything that comes out of our hose, again, is going into our system. So we can just represent that by Q. Right? What is the flow rate coming in? That's, in theory, distributed across some area, coming in at some average velocity. But we're just not even worrying about any of that. We're given a flow rate. We're given 20 gallons per minute. So the assumptions that come along with, or the simplifications that come across with this uniform flow of integrating across our control surface, we want to have those. Okay, so yes, we're going to assume that we have uniform flow. Is it steady? No. Right, so we've got a deforming control volume. We're adding mass. The amount of mass stored within our control volume is changing with respect to time. So no, that's not a steady flow that we want to consider here. Is it incompressible? Yeah, that seems reasonable. We don't know anything about the density. We're just filling up this cone, so we're going to assume incompressible flow. Do we have one inlet, one outlet? No, we've got one inlet. We don't have any outlets, right? Oh, I should have crossed that out. Do that quickly. Okay, so we're not going to assume one inlet and one outlet. So when we go through our, take our equation and simplify it down, this is what I came up with. Okay, our unsteady term, we need to hold on to that. I'm going to talk about this more in just a second. And we have one inflow, which gets a negative sign. Okay, and as I pointed out, though, we don't know this velocity in, we don't know this area in, so we can just represent that as a Q. Okay. Further, since we're assuming incompressible flow or a constant density, we're adding up this density over and integrating it for the entire control volume. That is simply the mass within the control volume. Okay. So our first, our next step here in the relationship, I've concluded that the change in mass in the control volume with respect to time is equal to the volume or the mass flow rate coming into our cone. We also said, though, this could be incompressible. So if I cancel out the density here, I can cancel out the density within that mass term, or take the mass and divide it by density, and I come up with a relationship like this, right? Where I can conclude that the change in volume with respect to time is equal to the volume flow rate, represented by this Q. Okay, I'll let you take it from there. Okay, from here you don't want to separate variables and integrate. And again, this is one where the answer is somewhat obvious. If you go through your unit conversion, you should be able to just immediately predict how long is it going to take to fill up a tank of some known volume when you're filling it with a hose at a constant and given flow rate. But can you get there both ways? Can you get there just by looking at it with logic, and can you get there by going through this systematic approach? And just to save you a little bit of time and make sure that we all use a consistent method, here's the volume, the equation for a volume of a cone, pi r squared times h, which in this case is going to be our 5 feet, divided by 3. Okay, and that gives you a volume in cubic feet. So be careful because your flow rate wasn't given. In feet, right, our cubic feet, we've got an expression there with gallons. Okay, so that brings us to a conclusion of this lecture. That's all we're going to talk about lecture-wise, at least, with respect to the continuity equation. We can kind of come back and tie up any loose ends on this on Monday as we transition into the momentum equation. And then this will be included on our next quiz in addition to exam 2. So give all this stuff a shot, try to work on those problems, and then we'll come back and make sure this stuff is tight and we're ready to move on next week.